Great. Thanks for the invitation. It's really a pleasure to be here. So as you know, the Simons is running these two programs in parallel this term, one on polynomial systems, or I guess algebraic geometry and complexity, and the other one on graph theory. So this talk is a little bit of both. I mean, there's, as we're going to see, some interesting things that relate polynomial systems with graphs, and I'll try to explain a little bit what this is. So everything that I'll say is joint work. It's really the work of my student, Diego Cifuentes. And I'll mention a few things about this at the end. So let me start kind of perhaps very quickly with somehow what the theme of this is, which is, let's imagine that I have a polynomial system that I'm interested in solving. So I have m equations in here in n variables. And what we're going to do is we're going to associate to my system of equations a graph. And somehow the way that we're going to construct this graph is pretty simple and pretty natural. So what I'm going to do is I'm going to take each equation. I'm going to look which variables appear in each equation. I'm going to draw a clique for each for that set of variables. So simple example, let's imagine that this is my set of generators in here. So my first generator in here has a variable 0, 1, and 2. So I'll just put a clique, this triangle in here between variables 0, 1, and 2. I'll do the same thing for my second generator, 1 and 2. This gives me the edge that I already had. And the same thing I do for the other ones, and I obtain this nice graph over here. So if you want, I'm just abstracting some combinatorial properties of my polynomial system just into the graph. So in a sense, what's interesting about this is that I only retain information of which variable is talking to which variable. And that's really the only thing that this graph knows. And there's a lot of very natural questions that one can ask in this situation. So to what extent the structure of this graph actually helps me to solve this system of equations? And of course, I put solve in there, emphasized in quotation marks, because there's many notions of what do we mean by solving a polynomial system. For instance, let's say, perhaps closer to this talk, is let's say that I want to compute a Grosvenor basis. Or perhaps I want to do something better than a Grosvenor basis, something different. To what extent I can do operations in here that will preserve the structure, the sparsity in particular of this graph. Imagine that this graph is extremely sparse, and I don't want to, new polynomials to appear that mix all my variables. I really want to keep things sparse to some extent. And somehow, of course, complexity questions. I mean, to what extent, perhaps if this graph is nice, then this will allow me to solve things in a nice way. This is a huge subject. I mean, somehow this is something that people have looked in a variety of subjects, not necessarily in algebraic geometry, but in many, many different frameworks. So if you're coming for numerical and linear algebra, you've seen this many, many times. I mean, the structure of, for instance, a matrix, when you do Cholesky factorization, you factor. Yeah.
So just a quick question. I should ask, so you don't allow multiple bonds if they...
I don't care. In this version, I don't care. I just write a graph. There's more sophisticated versions where I put hypergraphs. You can overload this in whatever ways you want. In here, I'm just doing 0 to 1. Right, and as I was saying, this appears in numerical linear algebra and graphical models. Statistical graphical models is a huge subject called graphical models. There's a beautiful area called constraint satisfaction that sometimes you study general constraints between variables and somehow these same kind of things, data-based theorem, and something that's common to all these areas, something that has appeared in unifying notion for all this stuff, is this the notion of chordality and the notion of treewidth. And I'll explain what those is, at least I'll give you a crash course in 2 minutes. And there's a lot of names associated to this depending on which community you like. In particular, I guess closer to the math side, of course, Graph Minors project, all the Robertson-Seymour stuff. Actually, paper 2, the second of their 22 papers that they wrote with the title Graph Minors, is exactly about the algorithmic consequences of having small treewidth. Right, but again, and I'll tell you, I'll condense in one sentence if you want the content of these 20 years of work. So remarkably, and at least for us it was kind of interesting, that we haven't seen really work on computational for solving polynomial equations that exploits this structure. And if I'm wrong, please tell me, and we looked all over the place. And what we hope, really, is that this is a starting point to change this. I mean, there's a lot of very interesting work that comes out of essentially all the mantras, if you want, that people have worked in here. And what we want to see is to what extent this can be done in this case.
Well, I think there's something, people know it's better would say, but there's something, triangular sets or some sort of reduction, you get something in a form.
This is a more refined version. This refines this.
I understand, but that's the only thing that I can think of.
Yeah. Okay, so what's the idea of chordality? Chordality is a very simple property of the graph. There's many, many different ways of defining them. Let me define in the way that's going to be appropriate for me. which is the idea that we're going to have a graph. I'm going to, just like before, I'm going to index my variables from x0 to xn. These are my variables. And then we're going to define a notion. This is standard stuff. I mean, this is not our work, of course. There's a vertex ordering. We're going to order the vertices in a particular way. And if we're going to call this ordering a perfect elimination ordering if the following property is true. Ignore what it says over there. But the idea is I look at my variable xl. I look at all the neighbors of xl. And those have to form a clique. So then I take this vertex out. I remove it. And I do it again. I try to find another variable, my second variable. All the things that are connected to that one, they will have to form a clique. And then I take it out and I keep going. And if I can do this for all my variables, this defines a perfect elimination ordering. And a graph is chordal if and only if it has a perfect elimination ordering. There's other ways of defining it, but this is nice. Right. So again, zeroth order model, chordality is a nice property of a graph. Now, what do I do if my graph is not chordal? I complete it. I do a chordal completion. I add edges in such a way that it will be chordal, and I assign a parameter called the treewidth, which is going to be the size of the largest clique that appears in that chordal completion. Right. Again, digesting this for the very first time is difficult, so there's one picture that I wanted to have in mind, which is the following. Treewidth is a parameter of a graph, and somehow I can think of a classification of my graphs where in here I have treewidth equal to 1, and treewidth equal to 1 are exactly the trees, or forests if you want, unions of trees. All the way on the other side, if the treewidth is equal to n minus 1, what I have is a clique, a complete graph in n vertices. And somewhere in the middle, the treewidth can have different parameters. In particular, for instance, if I have a grid, the grid graph, this has treewidth, whoops, square root of n. When n is a number of nodes. There's a nice parameter that somehow quantifies, if you want, how close is my graph to being tree-like or being like a complete graph.
Is there a unique smallest chordal
Yes.
relation?
Yes, computing that is NP hard, but I mean, and for trivial reasons, just because everything is finite.
But it's not unique.
It's not unique. No, it's not unique.
Take an n
But the
cycle,
size is unique.
N cycle, any triangulation
Yeah.
of the n-gon. The boundary
But
of
the
an
clique
n-gon
number
is
is
made.
The clique number is unique. Yeah. Why we care about this? Because again, if I want to condense these 25, 30 years of work in one sentence, the idea is that NP-complete problems that you do on chordal graphs, on graphs of small treewidth, they become polynomial time solvable. The idea is if you want to do stable set, whatever you want, kind of coloring, whatever you want, and you do it on graphs of this type, and again, of course, one needs to quantify them, then they become, for fixed treewidth, they become polynomial time in the number of vertices,
So
or even linear times.
Is there an upper bound on the tree width of a planar graph?
Yes, yeah, there are bounds. Essentially, I think for planar graphs, you get something like square root of n. This is essentially okay.
For example, your last statement, you crack up any issue of scientific journal discrete math, and there'll be one or two papers on tree without
Sure.
as much as
Yeah. I mean,
It's really
the whole graphical models is about this. I mean, this appears all over the place. So, great. You learn about this. First thing that you want to do, let's solve polynomial systems. I mean, let's try to apply this to solve polynomial systems. Perhaps we can obtain some nice result. And it's more subtle than this. So the idea is that even, for instance, if I look at, so let me take the subset sum problem, right? I get integers. This is a problem of can I find the subset that adds up to a number, right? It's very easy to write a polynomial system like this one. The s sub i's are the partial sums in there. The graph associated to my equations, so in here in my equations we either have a 0, Sn, or a variable talks to its neighbor. Right, so the structure of the graph that I defined before that I would associate is exactly a path. But we know paths have tree with 1, they're trees. But of course subset sum is NP-complete. So somehow it's not quite true, this meta theorem that I was telling you before. When you look at polynomial equation, things are a little bit more subtle. Or there's things that have to be true for something like this to happen. And it's a little bit also worse, let me give you all the bad news at the same time, is that somehow in the linear situation, is also very different from the polynomial case, right? Because in the linear equations, somehow it's easy to do elimination in a way that preserves graph structure. That's exactly the notion of perfect elimination ordering, that I can do elimination and somehow I don't increase the sparsity somehow of a graph. But for polynomials, if you try to do many natural things like computing Grosvenor bases, that will destroy chordality immediately. So simple example, by illuminating, let me take these two polynomial equations. x0 talks to x2, x2 and x1 are talking to each other. And the point is, if I compute any Grosvenor basis with respect to any term order, whatever you want, then that will always contain the polynomial x0 minus x1. So any Grosvenor basis destroys the structure of a graph. I cannot hope to compute a Grosvenor basis with the same structure of a graph because there's no such thing. So perhaps we need to change things a bit. Good news. So the good news, or then this is essentially the content of this paper that we're finishing. This is really the master thesis of Diego, which is on the one hand to propose a chordal elimination algorithm, an elimination algorithm that takes into account this graphical structure and will allow us to say some interesting things. We're going to be conditions. I mean, as we said before, in the full case things don't work, or we have to be careful. So we're going to put conditions under which this kind of chordal scheme succeeds, computes what we want, and it's in a nice way. As a replacement of Grosvenor bases, we're going to be computing, I mean, we could compute Grosvenor bases, but that's somehow the wrong object to compute in this case. We're going to compute the elimination ideals of the maximal cliques. Somehow that is really the nice object, or a nicer object, and I'll try to explain quickly why is that the case. And as a result of this, I mean, very much in line with the kind of results that we were saying before, is that for a certain class of problems, we're going to have the complexity of, for instance, computing Grosvenor bases. This is going to be linear in the number of variables, although it's going to be exponential in the treewidth. Which again is very much along the lines of all these results that we were saying before, all the things in graphical models, all the things in, kind of all over the place. When you pay a price for treewidth, cliques are really the problem. And the number of variables is not really such big a deal because you can schedule computations in a way that kind of the number of variables affects you only linearly. And I'll talk a little bit about implementation and experimental results. Right, so again, I have 10 minutes. I'll spend 2 minutes on each. So what's the idea of, or the sketch, if you want, of how chordal elimination works is, to some extent, the natural thing that you would do, but you have to be careful with a number of things, and I don't have time in here to tell you about the subtleties. But the basic idea is really the following. What we're going to do is just imagine that you're computing the elimination ideals. So how you would compute the successive elimination ideals. Remember, I have a perfect elimination ordering. I have my graph that's coming from a polynomial system. I will compute the chordal completion. This chordal completion has a perfect elimination ordering which is tailored to my polynomial system, right? It's not any elimination ordering. It's a particular one. So we're going to produce a sequence of ideals in there. Think about them as the elimination ideals, but they're not quite that. And the way that we're going to compute them is in the following way. At stage I, let's say that I want to eliminate variable x of L. So what I'm going to do is the following. I'm going to split my ideal into what, or the generators of my ideal, into all the ones that contain x of L, and all the things in the clique of x of L. That's what we put in J, in here. And K is all the remaining stuff. All the stuff that has variables in here, and perhaps some of these ones. And then I will just eliminate, again, this is a cartoon version, I will just eliminate from this x of L, variable L. So essentially I get rid of this, and of course, because of chordality, the polynomials that result in there, they only contain things in this clique. Right? I mean, that's exactly the property of chordality. When I eliminate this, somehow I shortcut all the things, and I'll just have polynomials in here. So what's important at this point is that the graph structure is preserved. As I move from one ideal to the next, I don't make the graph sparser. Sorry, I don't make the graph denser. I keep the sparsity of the graph. Right now, if you just try to do this, then it doesn't necessarily work. I mean, so there's conditions, of course, that we will need to put for this to succeed. By succeed, I mean that essentially that I'm computing the right variety up to, actually the right variety, the right projections on the variety. And let me give, again, I don't have time to tell you the specific details, but for instance, there's one class of results that we can write where, for instance, we can put some zero dimensionality assumption on the projections on the maximal clicks. Again, some technical condition, don't worry too much about this. But in particular, this is always satisfied for finite fields or 0-1 problem. Some condition, essentially think about it as zero dimensionality, and in this case, this method of eliminating things will actually work. And we have a slightly different version, actually a more general version that does not rely on zero dimensionality, but it relies on the structural property of my generators. We call it simplicial, and again, somehow it's a property about somehow terms having a particular type, the leading terms having a particular type. And in that case, again, which is not about zero dimensionality, we have, again, that this Chordal elimination exists. What's a high-level idea? How does one prove these kind of things, or why these things work? So they really have is somehow the iterated version, an iterated version of the closure extension theorem that you learned when you first learn algebraic geometry, computational algebraic geometry, how to extend a partial solution to a full solution whenever you eliminated some of the variables, right? That you need some leading coefficients to be non-zero. And the difference in here is that you don't need to do it once, but you need to do it in an iterative way. And somehow that's where these kind of conditions come into place. And chordality. That's the other second piece that will tell us that we can do this in a way that will preserve the structure. So again, high-level version, there's this Chordal elimination, and there are certain conditions what you compute is exactly the right thing up to, again. In the general case, if we don't put assumptions, it may fail. There's simple examples that will show this, and if we have time in the end, I can come back to this. Right. Think about this as one result about zero dimensionality. The other one, it relaxes zero dimensionality. We still put some conditions on my polynomial system that will guarantee that this kind of iterated thing will work, will compute the right thing, preserving structure all the way to the end.
That's not zero-dimensional.
Sorry?
The bottom.
In here? No, in here I'm not working over 0, 1 or anything like this, and this is not.
I thought this implies zero-dimensionality. The prime numbers.
No, it's a little bit different. I think it's not, I mean, it looks like the condition for zero dimensionality, but it's not. That's for every variable, there's a leading term. Yeah, this is a bit different. Because you require this for the generators, not for a Grosvenor basis. Okay, so what about, I said, perhaps Grosvenor bases, I mean, at least in some of these cases, we don't like them, or they're kind of somewhat problematic because they destroy chordality. And the question is, can we do something nearly as good and try to preserve as much as possible the graph structure? Again, think about the situation where we have extremely sparse graphs, for instance, and I don't really want to mess it up in a particular way. So it turns out that what we would like to do is to compute the elimination ideals for the maximal clicks of my graph. And something that's very nice about the Chordal graph, as opposed to an arbitrary, I could try to do this for an arbitrary graph, but there could be problems. And the two problems would be that if you try to look at the maximal clicks of an arbitrary graph, in general I have exponentially many. If you look at an arbitrary graph, the number of maximal clicks can be exponential. Chordal graphs have at most n maximal clicks. And the other thing is that if you try to do this for an arbitrary graph, you run into a local global problem. That you can compute the ideals for your clicks, for your individual clicks, but then you cannot glue them together. And what happens at Chordal graphs is that somehow, again, let me be very imprecise, but you don't have topological problems. You can glue these, the maximal clicks in a particular way, something called the tree decomposition, and somehow all these solutions will come out nice. And I'll show an example in just a second. Right, and why do we care about this? Because somehow this union of the Grosvenor bases, for instance, of the individual clicks, has nearly the same information. It's a lot nicer, it's a lot sparser. And as I said, or I hinted, we can compute these maximal clicks from the output of this Chordal elimination algorithm. And somehow this is really the insight. That what happens in this case is that instead of studying the variety somehow in the full space, what I really want to understand are the coordinate projections. The projections on the subspaces defined by the maximal clicks. And the chordality structure allows me to glue them in a nice way that I could not do if we didn't have some kind of nice property in that. Here's an example, for instance, that will again at a high level illustrate what I want to do. So let's imagine that I have this graph in here, This is described by these equations, right? What these equations encode, for instance, are just colorings of this graph. Think about my graph, it's a blue one without the green edges, right? So that graph is not chordal. We do a chordal completion, which is obtained by adding these green things, and now I have a chordal graph. This graph, I can just enumerate the maximal cliques, which we can do in polynomial time. These are the maximal cliques of this graph. And then what we can is compute using something, it doesn't matter, what the clique elimination ideals are. So these are the elimination ideals where my variables are restricted to the maximal cliques. So for instance, this H5 corresponds to clique number 5. And what this is saying is that the projection on my variables will give me exactly this ideal. These are exact. And what happens in here is that, for instance, if I want to, let's imagine that I want to solve the polynomial system. I can just solve independently for each one of those ones. All the solutions, I can glue them in a nice way, and chordality tells me that I'll have a way of gluing them and I will not run into any kind of problems. And again, the theory of how to do this is all these, tree decompositions of chordal graphs, so that it's not terribly complicated. But the real point, the geometric picture I want you to have in mind, is that if I want to think of this variety in here, all the colorings of this graph, I have 1 million points in here, right? All the possible colorings in there. But their projections on sets of small size, they're small. Because when I look at every clique, the size of that projection is at most the number of colorings for this number of variables. Right? And it turns out that there's a smart way of doing this and gluing them. Well, okay. I have one slide in complexity and one slide on the theoretical on the experimental results. So as I said, somehow what we obtain, again, very much in lines of kind of the theme, if you want, of treewidth, is that in nice cases, and I'll hand wave out exactly what we mean by nice in here. The complexity of doing all this is linear in the number of variables, although it's going to be exponential in the treewidth. Right? So in particular, for instance, the complexity of finding the elimination ideals, in this case is going to be exactly of the form O tilde, so this hides polynomial terms in the treewidth kappa, which is going to be linear in n and exponential in the treewidth kappa, and in here Q is somehow a parameter that determines how nice my ideal is going to be. Again, this is like a general version. I haven't defined what this is, but if you want to make it very concrete for a nice polynomial system of the type that we've seen before, we can translate, for instance, if we pick particular polynomials, into the statement that if you want to count, for instance, the number of colorings of a particular graph, Q colorings, if you want to color a graph with Q colors, then you can just count them exactly by counting the solutions of a corresponding polynomial system, and that will give you something which is, again, linear in the number of variables and exponential in the treewidth. Right, so that's fine. Okay, just a couple of things about implementation. So Diego implemented this in Sage using singular and this polybody solver, which is really for things over F2. In the paper, we analyze a few examples from graph colorings, the one I described before, something from crypto and network organization, whatever. I'll only describe in some level, I think, these two. So let me tell you what this is a particular example of a baby version of what's called the AES, the Advanced Encryption Standard. So this is a small or relatively small polynomial system. I think the largest that we solved in here has 288 variables and 528 equations. And again, ignore the numbers. Let me perhaps, we have more extensive tables in the paper, but let me tell you what the high level version is in here. And this implementation is not terribly optimized. I mean, this is really... so for small problems, of course, Grosvenor bases will actually outperform the kind of things that we can do, just because problems are not big enough that you can start seeing the exponential versus linear or small behavior. But as the problems get bigger, in this case, for instance, for n is equal to 10, then chordal elimination scales better. I mean, or we see, for instance, that these two methods, for instance, let's say this one in here, you need to abort. I mean, we're aborting in here in terms of memory, and in here we really don't have a problem, and we could solve, I think, much bigger things. Also, they're a lot more memory efficient because the memory requirements that we have in here, they're bounded by the size of the maximal click. I mean, that's really what bounds. So in a sense, you don't depend in a very sensitive way in the number of variables. The same thing, something quite similar is for the, so this was an example over F2. If you do things over the rationals, in this case, Diego did an example also based on sensor networks. We have nice equations of this type, and I won't describe them. I think many of you have seen them before. There's kind of two regimes in this case, whether you're in the under constraint situation or the over constraint situation. In the under constraint regime, what they're doing is certainly better. I mean, it doesn't even make sense to compare it. In the over constraint regime, then the methods are competitive. So this is just a plot of the relative timings of one method versus another method. And as you can see, again, we're in somehow in the bad regime for us. But even in here, kind of the timings are, I think, fairly similar. And there's a number of instances in particular that we can solve much, much better than these other methods. Again, it's not a complete analysis. This was really just a start of trying to see how well these methods work. So I need to wrap up. That's what they're telling me. So what's the summary? This chordal structure is an enormously theoretically and practically interesting feature of polynomial systems, and we definitely need to exploit this. If we put the right assumptions, which again, something that's very distinct from the combinatorial situation, is that we don't need just treewidth. We need something else about the geometry of these problems. I mean, we have this way of imposing this, perhaps there's better ways. Then things become tractable. It yields practical algorithms. They're competitive with techniques in a relatively small amount of time, and they're implementable. And actually, those form the core of kind of extremely efficient methods, for instance, for satisfiability or a whole bunch of other areas. And one of the things they're trying to do is really to understand to what extent one can extend this, not just to the Grobner situation or the elimination type situation that we're doing in here, but actually to the full spectrum of numerical methods for polynomial equations. If you want to know more, Diego's thesis should be somewhere. I guess you can ask him. And also the paper, we hope to be, we're hoping to get it before the talk. It will be done by the end of this week. Otherwise, it can be.
Thank you.
Couple quick questions, Josh?
When you say you solve click by click, so you have an ordering of the click. You start, for example, you solve the first click, and then you have a variable which intersects with the next click, right? So for the next click problem, you fix the value that you found for the solution.
If you want to solve, yeah, this is a standard thing in constraint satisfaction. I mean, that's exactly what you do. You propagate on the click tree, click by click.
You have to do it sequentially.
You have to pick any ordering. In particular, if you pick an elimination ordering from the beginning, this induces an ordering in the click tree. So there's a number of different ways of doing things. Yeah.
You're saying you can't do all the quick problems individually, separately on different processors at once?
If you want, you could do that, but then you have to combine, and then you combine the solutions independently. I mean, that you can also do that.
Yes, Mike.
Maybe you said it, but what's wrong with the equations for the subset sums? Which, the example.
Oh, that's a very good question. So what's wrong in here? Many things, right? So first of all, remember I said that there's two properties that we care about, right? So the two properties are, on the one hand, am I computing the right thing? And in this case, this is fine. If I just go in there and eliminate one variable at a time, this is fine. But the problem is that the complexity of the ideals that I get in the middle, they get bigger and bigger. Right? So the projections, if you want, on this variable, on the partial sums, they're not bounded. The projections in here increase in degree. Right? If I look only at, for instance, for all possible assignments, how large can, kind of S15 be, then I'll have 2 to the 15 possible values, unless something particular happens. And one way of doing this is exactly what you do when you restrict the domain. But notice that in here my variables are not 0, 1. These S sub i's have not 0, 1 variables. Right, they're the partial sums.
Yes.
In the problem of graph coloring, you are describing, correct me if I'm wrong, an algorithm that is polynomial time in the number of vertices where the exponent depends upon the tree width.
Yep.
Here. And does this work for all graphs, or do the conditions?
All graphs of tree width less than or equal than something.
Yes.
Yeah.
the conditions are actually met in this particular case.
Yeah. All the because that's essentially a 0-1 problem, like kind of.
Sure. Projecting down any particular ideal is going to always give you some very small set because it's just a finite set anyway.
You have a quick question?
Yeah, a quick question. I wonder, do you have like a family of polynomial systems where we can show what happens actually? One looks at the structure and then somehow the treewidth is small and then you...
There are certainly families of...
I mean
there's
families that you can treat. I mean, I know this concept of treewidth, but I wonder in this context of polynomial equation solving, do you have like a family that you can do?
So for instance, and again, we're really looking exactly at the...
something I can understand. I mean, something with the meaning.
So for instance, I mean, one thing that happens in here, when you look at these problems in here, again, we need to check this, but what happens when you look at these polynomial systems, the complexity of the... so you have a graph somehow that depends on n, on the number of rounds of this crypto system. And the complexity in here seems to be independent of n. So even though you're getting more and more rounds of the same problem, this is not affecting somehow this affects in an exponential what am I trying to say? Yeah, so you have a family of polynomial systems in here, and the treewidth is independent of n. That's exactly what I'm trying to say.
But my understanding is you have like your input system and is somehow sparse, but then the sparsity you describe in a more sophisticated way using these ideas of bounding treewidth somehow.
Right.
And then you have some other conditions that you did not show. And if this treewidth is small, then you can do it efficiently.
That's right. Yeah. Again, that by itself is very much in line to, I mean, in a sense, for the discrete or the case, we knew that. I mean, we know this since the 70s, right? 80s.
Yes.
That, kind of, if you want to do coloring, if you want to do a number of things of this type, kind of, I mean, number of variables doesn't really matter.
Are the other conditions other than treewidth easily detectable?
Oh yeah, you can just check them. Yeah. I mean, there are conditions just on the input set, on the input generator, or the generators of ABL. Yeah, and they're automatically satisfied again in this kind of 0-dimensional situation.
Okay, to keep on schedule, let's thank Pablo.